Hey guys, so today we're going to start some application problems around maximum and minimum questions. So the last couple of days, we have focused on trying to find the absolute max, the absolute min, local maxes, and local mins directly from our equation. Okay, again, from a calculus perspective, we are finding those points without technology, which is what they did 300 years ago, right? 400 years ago. So it's pretty cool. There's going to be some of the questions that you look at today and tomorrow. This is a 2-day lesson, okay? So I'm going to go through a bunch of problems with you today, and then you can have today and tomorrow to kind of work through the rest of the homework, okay? So you're going to come to a couple of the problems. I know we've had this conversation before, but where there are other different ways to solve it. There are some questions that we could have asked you in 20-1 and you could just look at it as it's a quadratic system of equations, which is great, but that's not what we're going to do. We're going to look at these now from how would I solve it from a calculus perspective, okay? So you want to keep that calculus thinking cap on your head the whole way through and say, how do I solve this from the lens of calculus? Okay. Now, when we go to do that, there's essentially kind of 5 steps that we want to take as we go through. So the first is just to set things up. You want to draw a diagram, define any variables that you're using. So let x equal this or let y equal that or whatever. State what is given and what is to be found. Okay. Very similar to how we started a related rates question. Number 2, derive an equation that you could maximize or minimize. And often you have to make the equation up yourself, given whatever you have. Number 3, make sure you have one variable. The equation from part 2 must only have one variable. And again, we ran into similar conversations when we did related rates and when we did related rate problems. Remember, the one I'm thinking of often was with the cone, where we had the volume of a cone involved the radius and the height. And so we represented one in terms of the other so that we could just have one variable there. Okay, you may require a second equation that can be used to substitute into the max or min equation. And then you're going to determine and test the critical points. So remember, the critical points are where we will have local min or maxes. And that's where either the derivative equals 0 or the derivative doesn't exist. So you're going to solve for the critical numbers and then test the critical numbers as well as any endpoints that you have. Okay, and then once you've pulled all that together, obviously you're going to answer the question. Okay, so let's try a few together. The first one we're going to do is determine 2 numbers whose product is 4 and whose sum of squares is a minimum. Now, you could have solved this from 20-1. I could have asked you this exact same question, and you would have created a quadratic that you write in vertex form and complete the square. Okay, because when you complete the square, the vertex tells you what your max or min is. That only works if you have a quadratic. And just because we have a quadratic doesn't mean we're going to answer that way. We're going to answer from the lens of calculus, okay? So my equation that I'm going to start with, I needed a product of 4. So x is my first number, y is my second number, and I said x times y is 4. I'm just going to hide myself here for a second because I might be covering up that equation there. So x times y equals 4. So now I'm going to rewrite that in terms of x. So I'm going to say y equals 4 over x. So the equation I'm going to deal with is y equals 4 over x. Okay. Now I'm looking for whose sum of squares is a minimum. So that would be x squared plus y squared equals some sort of minimum. Okay. Well, this is what I want one variable for, and this is why I just spent that time writing this in terms of y. I can now make that substitution in for this y here. Okay, and so I'm going to be left with x squared plus 4 squared over x, or 4 over x squared. Sorry, I said that backwards. That there's technically brackets there, right? So 4 over x squared equals a minimum. Okay, we're eventually going to have to take the derivative of this, right, and set the derivative equal to 0. So the easiest thing to do at this moment would probably be, why don't we call 4 squared 16, and let's just call this x to the negative 2, so that I have one line there instead of dealing with the fractions. Now I'm going to go ahead and take the derivative and set it equal to 0. Okay, so the derivative would be 2x, and then this would be negative 32 x to the negative 3. Now, I want to make sure the derivative is written in a simple fractional way, because I need to look for those points where the derivative doesn't exist as well, right? So this negative 32 x to the negative 3, that'll be negative 32 over x to the 3, and then I want a common denominator. So what I did to get that was I just factored out 2x to the negative 3. That left me with x to the 4 minus 16. Okay, and then this x to the negative 3 can come to the bottom. Okay, I also factored the difference of squares that I saw. So x to the 4 minus 16 would be x squared plus 4 and x squared minus 4. And then x squared minus 4 would break down one more time into x plus 2, x minus 2. Okay. Okay, so I didn't write this as a one pretty fraction. I just grabbed my critical numbers from here, but just to show you where my critical numbers come from, my critical numbers come from, this guy would be negative 2, this guy would be positive 2. I can't get a 0 here, right? Because I'm squaring something and then adding 4. And then this is an x to the 3 on the bottom. And so if I had an x to the 3 on the bottom, x also can't be 0. So my critical numbers are negative 2, 0, and 2. So I'm going to take those critical numbers, I'm going to write them on a number line, and I'm going to test on either side. So I need to test a number less than negative 2, something in between negative 2 and 0, something in between 0 and 2, and something greater than 2. So you want to pause me and do that yourself. Okay, and you should end up getting negative, positive, negative, positive. We're looking for a product whose sum is a minimum. So really, we're looking for decreasing to increasing right now. And that would happen at negative 2, and it would happen at 2. Okay, so now that we found the numbers we want, we need to get the corresponding y values that would go with them. So I'm increasing between negative 2 to 0 in union with 2 to infinity, and I'm decreasing from negative infinity to negative 2 in union with 0 to 2. If I go back to that y equals 4 over x, okay, I'm just going to write that over here for you for a second. Y equals 4 over x. Okay, if I plugged in negative 2, I would get out 4 divided by negative 2, which is negative 2. And if I plugged in 2, I would get 2. So the two numbers are negative 2 with negative 2 and 2 and 2. Okay, so I have a local minimum at negative 2, negative 2. And another local minimum at 2, 2. Okay. And so remember that last thing was I do give some sort of a conclusion. The two numbers are negative 2, negative 2, or 2 and 2. Okay. Okay. If 2,700 centimeters squared of material is available to make a box with a square base and no top, determine the largest possible volume of the box. Now, again, you've done questions like this before. We've probably asked you questions like this in grade 10 for factoring. We've probably asked you questions like this in grade 11. Now we're looking at it from a calculus perspective. So you've got this base of your box, which would be x by x because it's a square. And then you're going to multiply it by some sort of height. And all together for surface area, you've got 2,700 centimeters squared available to you. Okay, so the first thing you want to do is set yourself up, draw yourself some sort of a picture. So I've got x by y here instead of h, same thing. Okay, Okay, so what sorts of things do we know? Well, we know the surface area is available to us. Now, the surface area is actually going to be this front square here is x by y. I'm just going to hide myself in case you can't see me there for a sec. So this front square would be x by y, and I would have 5 of those. 1, 2, 3, 4. No, I would have 4 of those. Sorry, because I don't. Yeah, my bad. I'd have 4 of those, and then I have 1 x by x on the bottom. I don't have a top to this guy. Okay, so the surface area would be my x squared. That's the one on the bottom, and then 4 x by y's. Okay. Okay. Now I need to get rid of that y. So I need to come up with some other way of representing the y. So I'm going to use this guy to get y by itself. So I have 2700 equals x squared plus 4xy. I'm going to subtract x squared and divide by 4x. Okay, and that gives me y by itself. So I used this piece that I knew the surface area. I used that piece in order to get an equation that I could isolate y for and substitute into the equation I actually want to work with. The equation I actually want to work with is I'm trying to figure out the largest possible volume. So the largest possible volume will be x by y. So x squared times y. But now I'm going to replace my y here with, or replace that y with this guy here. Okay. And so that becomes x squared times 2700 minus x squared all over 4x. Okay, so if I'm going to go x squared times this guy, well, the first thing I can see here is one of my x's will divide out. So I could take that guy, and one x has divided out. So now that'll be 2700x minus x cubed all over 4. 2700x minus x cubed all over 4. Okay. All right. So this is the guy I now want to try and do something with. Okay. So what I've done is I've gone to, I wrote my 1/4 to the front, and then I took the derivative. So the derivative of 2700x would just be 2700, and the derivative of my negative x cubed would be negative 3x squared. So this guy here is now the derivative of my original v of x. Okay. Now, when does that either not exist or equal 0? That's what I'm looking for critical numbers. It will never not exist, but it will equal 0 if I just set this guy equal to 0. So 2700 divided by 3 is 900, and then the square of 900 would be 30. So I've got plus or minus 30 as my critical numbers. Those are the ones I want to test now. Okay. So let's go ahead and do that. We're going to draw a number line, mark my negative 30 and my positive 30. Test something lower than negative 30, in between negative 30 and 30, and higher than 30. Remember, when you test, you're testing them into the derivative because you're trying to figure out if the derivative is positive or negative. You should be getting negative, positive, negative. Now, we were looking for the largest possible volume. So we're looking for a maximum, which means we want to go from increasing to decreasing. And so we can see that that maximum occurs right at 30. Okay, so if I now know the maximum occurs at 30, I need to plug that back into the original and see what y value goes with it, right? So I'm increasing between negative 30 and 30. I'm decreasing from negative infinity to negative 30 in union with 30 to infinity. Okay. Now, just for clarification, this increasing and decreasing comment does not take into account the fact that we're talking about a real life box, right? There are restrictions on the domain that we're not talking about right now. That's okay, because the maximum point we found, we know exists within the allowable domain, okay? Okay, and so then I'm plugging in that 30, and I get out y is 15. So the dimensions are 30 centimeters by 30 centimeters by 15, which will give me the largest volume of 13,500 centimeters cubed. Okay, 13,500 centimeters cubed. Okay, next question. Determine the point or points on a curve y equals x squared that is closest to 18, 0. Now, I want to just kind of map this out for you so that you understand what's happening. So this is y equals x squared. Okay, and then over here, we would have the point 18, 0. And what I'm trying to do is say, okay, which line could I connect back to y equals x squared so that that line is the smallest number possible, essentially, okay? Now, how would I do that? Well, I'm going to call this point here x comma y, and then I get a cute little triangle. So I'm just going to use the Pythagorean theorem, right? What's the distance now from here to here? Well, from there to there, it would be 18 minus x, because I'm at 18 and I subtract x to get back to there, okay? What's the distance from here to here? Well, essentially it'd be y minus 0. Okay, so I can end up going d squared, I'm just gonna call this guy d here, d squared equals 18 minus x squared plus y minus 0 squared, okay? So I'm gonna say let the point be x comma y, and then I just create my Pythagorean theorem. D squared equals 18 minus, sorry, x minus 18 squared plus y minus 0 squared. That's where that equation is coming from. Okay, now I got to square x minus 18 squared. So that's x squared minus 36x plus 324 plus y squared. Now remember, I want one variable here. So y, I need to have another way of representing y. Well, I do, because y is x squared, right? That was the original equation. So I can replace my y value with x squared. And so then that will be x squared squared, which will give me x to the 4. Okay, so I end up with x to the 4 plus x squared minus 36x plus 324. Okay, so now I'm going to go ahead and take the derivative of this. But remember, d is just some constant. So the derivative of a constant is, that's where you all yell, 0. So, so I'm going to go ahead and take a derivative. Sorry, take the derivative. So that will be 0 equals 4x to the 3 plus 2x minus 36. Okay. All right, now I have to go and try and factor this, okay? So I can divide everything by 2 just to make my numbers a little smaller. But still, I'm looking at some sort of a cubic. It's not a quadratic. So I need to find a factor. So I'm going to test some points. Remember doing this in 30-1. I'll go p of 1, p of negative 1, p of 2, p of negative 2 until I find a 0. Okay, it ends up being p of 2 is 0. So I know that x minus 2 is a factor. I've not done that on my slide, but I'll do it here with you just in case that's stressing you out. I don't want to stress you out. So let's do long division because synthetic division is fake. X minus 2 will go 2x cubed plus 0x squared. Remember, you always have to have a place value holder for each guy plus x minus 18. Okay, so what do I have to put up here so that I get my x cubed? I'm going to need 2x squared. 2x squared times x is 2x cubed. Then I would have negative 4x squared. I'm subtracting, so that's 4x squared. What do I have to put up here? Well, I'd have to put plus 4x. 4x times x is 4x squared. 4x times negative 2 is negative 8x. Subtract. 1 minus negative 8 is 9. I would need a 9, which would give me 9x minus 18, which gives me a remainder of 0. Okay, So that's going to give me x minus 2 times 2x squared plus 4x plus 9. Then I want to factor 2x squared plus 4x plus 9 if I can. Okay, so 2 times 9 is 18. Two numbers that multiply together to give me 18 and add together to give me 4 don't exist, right? I got 1, 18, 2, 9, 3, 6. None of that's going to give me 4. Okay, so that is in factored form. So the only 0 possible would be at 2. And so now I test that. Okay, so critical numbers at 2. I'm going to test it. I'm just going to hide myself here for a second. Test to the left and to the right. And I do get negative to positive. Okay, so I did want a minimum. So that makes sense that I get from negative to positive. So I'm increasing from negative infinity, sorry, I'm decreasing from negative infinity to 2 and increasing from 2 to infinity. I got a local max at 2, 4. And so, sorry, local min, I said max, I just listened to myself. Local min at 2, 4. And so the point 2, 4 is the one that will be closest to 18, 0. Okay, determine the radius and height of the right circular cylinder of largest volume that can be inscribed in a right circular cone of radius 6 centimeters and height 10 centimeters. So what do I have? Well, I've got a cone where I know the radius is 6 centimeters and the height is 10 centimeters. Okay. And then what I want to do is I want to inscribe a cylinder inside this cone. Now, when I inscribe, the word inscribe means that the edges of one thing are aligned with the edges of the outer guy. So maybe it looks something like this. Okay, where I have the edges of this cylinder now right with the edges of that cone. Okay, so what I want to do is I want to essentially just draw a cross section of this for my diagram. And that would look something like this. If I can get my mouse going here. Okay, so this is my cylinder, the blue guy in here. And I know the red guy is the cross section of my cone, okay? So I know that the whole height of my cone was 10. And so what I'm doing is I'm going to call the height of my cylinder h, which means this leftover piece would have to be 10 minus whatever h was, okay? Likewise, I knew that the whole radius of the cone was 6. So what I'm going to do is I'm going to call the radius of my cylinder r, which means this leftover piece here has to be 6 minus r, okay? And what I'm going to do with that is I'm going to start by making a ratio. And the ratio involves these two triangles right here. So let me just get some ink on. I'm going to take a look at this, h over 6 minus r equals 10 over 6, essentially, okay? So I did my little height over my little base equals my big height over my big base, okay? Now, I can cross multiply that and get h all by itself. So a way to represent h would be, I just took my 10 over 6 and reduced it to 5 over 3 and multiplied it by 6 minus r, so I could get h by itself. So h can be represented as 5 times 6 minus r over 3. That's going to be useful in a second, because remember, one of the things we want to do is we want to come up with an equation that only involves one variable. Okay, now, in order to come up with the equation, we need to think, what are we talking about? Well, we're talking about volume, and I want the largest volume possible for my cylinder. So the volume of a cylinder is pi r squared h. Now, I can't start taking the derivative here because I have more than one variable going on. So I'm going to use that h that I just figured out And I'm going to replace that h with that 5 times 6 minus r all over 3. Okay, now I have a way of representing the volume that only uses r on the right. Okay, so we can clean this up a bit. This is going to be 5 pi over 3 essentially, and then r squared, and then multiply it by 6 minus r, and I would end up with 10 pi r squared minus 5 pi r cubed over 3. Okay, so essentially, just in case I lost you there for a second, I took 5 pi r squared, multiplied by 6 and divided by 3. That's what gave me my 10 pi r squared. And then multiplied by negative r and divided it by 3. That's what gave me my negative 5 pi r cubed over 3. Okay. All right. So now I am ready to take the derivative of that. So this is going to be dv over dt, 20 pi r minus, this will end up being 5 pi r squared. So 20 pi r minus 5 pi r squared. Okay. And now I'm looking for the critical numbers. So I know I have the derivative. I had said dv over dt. Here it's written as the derivative. Doesn't matter, v prime. Okay, so now I'm going to set that equal to 0, and I'm going to solve for r. Okay, so there is an r involved in each of these, so I can factor out the r. I chose to factor out 5 pi with it just to make things a little easier to see. So if I factor 5 pi r out, I'd be left with 4 minus r. So again, remember my critical numbers come from when the derivative equals 0 or when the derivative doesn't exist. There is no spot here where the derivative doesn't exist, but there's 2 spots where the derivative equals 0, and that would be at an r value of 0 and an r value of 4. Okay, an r value of 0 and an r value of 4. So now what I'm going to do is I'm going to plot that on the number line. I'm going to check out things to the left of 0, things in between 0 and 4, and things to the right of 4. And I'm expecting that you're doing that and that you're pausing me. That's going to give me negative, positive, negative. Now, it said, what is the largest volume? So I am looking for a maximum point. So remember, a maximum point will occur when I go from positive to negative. So I can see algebraically that I would have a maximum at 4 here. Okay. So I know that my radius has to be 4. And then I threw this back up on the PowerPoint because if I know my radius is 4, I can actually plug that in and figure out what my h value has to be as well. Okay. So my h value ends up being 10 over 3. And again, I'm just plugging in 4 for r. 6 minus 4 is 2. 5 times 2 is 10. Okay. So now I know I need a radius of 4 and a height of 10 over 3. And then the question is, what is the largest volume? So I'm going to plug that back into that original volume formula and get the maximum volume will be 160 pi over 3 centimeters cubed. And then that will occur with a radius of 4 and a height of 10 over 3 centimeters. Okay. All right. Last question. A boat A is 40 kilometers west of boat B. If boat A sails east at 20 kilometers an hour and boat B, starting at the same time, sails north at 10 kilometers an hour, determine the time when the boats are closest together. Okay, so we need to draw some sort of a picture here. So we're going to start with boat A is west of boat B and is going to sail east. So boat A would be right here, and boat B would be right here. Okay, so boat A is 40 kilometers west of boat B, and what's going to happen is boat A is going to sail 20 kilometers east, so it's 20 kilometers that way. Now, remember, my fixed point here is really going to be where boat B started, and then boat B is going to travel this way. Okay, so what we're going to do is we're going to call boat A's rate negative, and we can call boat B's rate positive. Okay, now because boat A's rate is negative, how I can represent that is 40, right, minus however far it's traveled, because that means that distance will be getting smaller, closer to where that fixed point was. Okay, so boat A is going 20 kilometers an hour this way, and boat B is going 10 kilometers an hour that way. Okay, so what brings all of this together if we're looking at the distance boat A is traveling and the distance boat B is traveling and the distance that they are apart from each other? That brings in all three sides of a right triangle, which means the formula we're going to use here is the Pythagorean theorem. Okay. Just because you see a triangle doesn't mean you're using the Pythagorean theorem. If you see a triangle, sometimes you're using the Pythagorean theorem, sometimes you're using similar triangles. It depends on actually what you're trying to bring together. Okay. Okay, so I just got to get my mouse back in order here. Okay. So I've said d squared equals 40 minus 20t. Okay. And plus 10t squared, where t is your time, okay? So 40 minus 20t all squared, that would represent this guy. And 10t would represent this guy, okay? All right, so now I need to actually square that. So that's gonna give me 1600 minus 1600t plus 400t squared, and then plus 100t squared. So when I bring those guys together, I will have 500t squared minus 1600t plus 1600. Okay, I now need to take the derivative of that. So I end up with the derivative. Let me just go back there for a second. So the derivative would be 2 times 500, which is 1,000. Okay, minus 1600, and then I set it equal to 0, so I can solve for t. Add 1600 to both sides, divide by 1,000. T is 1.6. So 1.6 is my critical number. That's when the derivative equals 0. Okay, and so I'm going to test to the right or to the left of 1.6. I see I get a negative and a positive, which means I found a local minimum. Now, that's good because I was originally asked when are these boats closest together, so I should be looking for a minimum. Okay, and so I know these boats will be closest together when t is 1.6. Okay, so I go back and state my conclusion. The boats are closest together at 1.6 hours. Okay, it only asked me to determine the time. That's why I didn't go back and plug it into my original equation. I actually have the answer with the 1.6. So the boats are closest together at 1.6 hours. Okay. All right. So this is what you're trying for the next couple of days. You know, these things take time and they take some thought. I don't want you to get frustrated with them. Make sure you're asking lots of questions as you go. And I'm here to help, okay? You've got the answer keys, you've got me, you've got these video lessons. Use them all together so that you can feel really, really good about it. So your goal is listed here, and then you're going to, that'll be for the next 2 days, okay? So after that, we'll pick it up again on odd and even functions and asymptotes, okay? I'll see you there. Bye.